We will discuss about bending moment and shear force, part 3 here. Okay, bending moment and shear force diagram, part 3. We already had two parts of that. The second part is very important. So if you haven't watched the second part, please do not watch this video. Okay, so the second part is the basics of this video. So please do watch that. Okay, we'll do problems in this section. So the first problem is there is a cantilever here and there is a point load P acting at the tip. Okay, the length of this member, this beam is L. Okay, so in this case, how will this member, this beam bend? It will bend like here. See, it is fixed here, so there cannot be any rotation here. So because of this point load, it will bend like this. See, like this it will bend. So this is the elastic curve. We have already discussed about the elastic curve. Okay, so this will be a hogging moment. So hogging moment means what? Hogging moment. So hogging moment we represent as negative. So bending moment diagram will be negative. Okay, so shear force diagram we have to draw first. See, for shear force diagram, we have to find out the reactions here. Suppose we name it as A and B. We have to find out the reactions at A point. We'll have vertical reaction and a moment to resist this load into perpendicular distance. So that will be sigma f of y is equal to 0. Then this will become P, and because in order to resist this P into this perpendicular distance L, a moment like this should act, that is equal to PL. Okay, solving these reactions that we have learned in part 1. Okay, so do follow those lectures. So here we have a moment PL as resisting moment and a transverse force P at the support. Okay, so we'll have to draw the shear force diagram. So shear force diagram, we will have this as the axis. Above this is positive and below this is negative. So first of all, we have to trace the path of the load. Okay, that is the procedure. So see the load P here. This is moving up. So we have to trace it upward. We have to draw it upward. So this P is going upward. Then till it reaches here at this maximum, this value is P. Okay, to some scale we have to draw this. So this value will become P. Then after that, see, there is no other point loads or no other UDLs in order to reduce this value or magnitude of P. So this P will reach here. Until here, there is no other forces. But here, see this P, this is reducing this value. It is then it come back here. The P value here reduces it and it will come back to 0 here. Okay, so this is our shear force diagram. So inside we represent the sign. So this is positive. Okay, that is what I mean by saying the left portion upward and down portion downward. Sorry, the left portion upward and the right portion downward means positive. This is what it means. Okay, we are moving with respect to this load. So the left side it is moving upward and the right side is moving downward. So that means it's a positive shear force diagram. Okay, now we'll have to draw the bending moment diagram. Bending moment diagram. This also we represent like upper side is positive, lower side is negative. This is our axis. And here see shear force bending moment we have to represent. It is like this axis we are representing bending moment and this axis we are representing the axis. Okay, the direction like x direction that we are representing in this axis, and bending moment we are representing in y axis. So that is our bending moment diagram. So see, with regards to our x is like from 0 to L point. Okay, from 0 to L we are having x value. So see here, this value P, this axis here will be shear force and here it will be x. Here it is bending moment in y-axis, and in the x-axis it will be distance x. Okay, so in the bending moment diagram. See, bending moment diagram, we know that the elastic curve, see, it is like this. So see, and also we have learned about the what that parameter like 0, 1, 2 we have learned. If loading varying from 0, then shear force varies like 1, x raised to 1, and sorry, bending moment varies like as x square. Like that we have already studied. So see, this is a point load. So shear force diagram, see, it varies like a straight line. So bending moment diagram should vary like an inclined straight line. That is x raised to 1. Okay. So we already know these concept. Okay. So PL is acting here at this point A. So PL is trying to like give a moment, a sudden moment. So what will happen? Also, this is a hogging moment. Hogging is negative. So we have to draw it in the negative side. So there is a sudden moment. Okay, this is a straight motion. Sudden moment is there, and that value is PL. And this is a straight line, inclined straight line, and this is our end. See, in this end we don't have a moment here, that is a free support, so that will be 0 here. So we join like this. So we have understood, okay, understood this is a like a very simple problem. If it is varying like x raised to 0 here, then it has to vary as x raised to 1. And we have a certain moment PL here. So suddenly it will have a jump at this point A. And we know that this is a Hawking case, so it will be negative inside. Okay, so that is it. I hope it's clear. Now the second one. A cantilever subjected to UDLW per meter run. Okay, this is the length L. So W per length. Okay, so this case, how will we solve it? See, you have a UDL. The free body diagram will be something like, because of this UDL, we have W per meter length. So the total load will be WL, that is W per meter length into total length. So that much of reaction is needed in order to make sigma f of y is equal to 0. From this, we will get reaction as WL. Okay, then you will have a moment in order to resist. See, the load is acting like this, so the moment should act like this. So what is the moment acting? Load into perpendicular distance. See, the load we have W per length into L, so WL is the load, total load, into centroidal distance will give you the moment. So length is L, means centroid is at L by 2, so L by 2. So WL square by 2 will be our moment. So this value is WL square by 2. Okay, this is the free body diagram. Also, from the figure, we will understand that the elastic curve will be somewhat like this. It is fixed here, so there is no rotation, and because of this UDL, the member will go like this. Okay, so this is the elastic curve. So we will first have to draw the shear force diagram. Shear force diagram. So see, if you draw like underwise, like this, then it will be very simple to understand. Okay, I'm drawing below this my beam itself. I'm drawing the shear force diagram. This is our axis. Here the top side is positive, bottom side is negative. See the force, the WL is acting upward. Here there is a WL, here there is a moment WL square by 2. So WL is acting upward. So we will have here WL value. So inside will be positive because the left side is moving upward. Okay, then what will happen? This is the UDL. So UDL we will have, if it's a UDL, then it is of x raised to 0 uh, value, then shear force diagram will be x raised to 1. So it will be an inclined straight line. So it means that it will now incline. See here at that tip we don't have any force. So it will be 0 value here. So it will go like this. Okay. we can calculate the net force here. That will be WL into WL minus W per length into L. So WL minus W per length into L will become 0 here. So that value is 0. Okay. So that is the shear force diagram. Then bending moment diagram. See, bending moment diagram, we have a sudden moment here, WL square by 2. So this is a hogging case. So it will be negative. So we have to draw it in the bottom side. Okay, so bottom side we have a sudden moment WL square by 2. Then see, since shear force is a inclined straight line, then bending moment diagram should be a square parabola, or it should vary as x square. So we will have, see here at this tip, at this point, and if you name it as A and B, at this B point, we don't have any moment acting on it. So the value will be 0 here. So we should join it like this. It will join, we can join it like this. Okay, it varies from WL square by 2 at one end to 0 at another end. And this will be negative because it is a hogging case. Okay. So I hope you understood this. Then the next problem, third one. This is a moment is acting at the tip of a cantilever. See here, because of this moment, we don't have any transverse force developed or reaction force here. Okay, only moment will be there. So moment will be like, if this is acting clockwise, then moment should act in anti-clockwise direction in order to resist this. So shear force diagram, we have shear force diagram. There is no force, so 0 will be the value. So this is a case of pure bending. Only bending is acting. Pure bending case is bending moment is acting. No shear force is acting. So this is a case of pure bending. Actually, in real structures, it's very difficult to find pure bending because in all the members, self-weight will be acting. And self-weight acting means that there is always a transverse force. So if there's a transverse force, then shear force will always be there. So pure bending is very difficult, or it's not possible in real structures. Okay. So here a bending moment diagram. Bending moment diagram, upper side we are putting positive, lower side we are putting negative. See, because of this force, how what will happen? See, the moment will be like, will cause it like this. See, just putting like this. So this moment is acting like this. So it will be a hogging case. So it will be negative. So we have to draw it in the lower side. See, a sudden moment is the M, and it goes like this till it reach here. There is no other moment in order to reduce or increase this moment. Till it reach here where a moment M, it pushes it to its original path. That is 0 point. Okay. So that is the case. Here we have to put it negative because this is a hogging case. Hogging case. Okay. So this is a case of pure bending. Hope you understood this case. Okay. Then the next question. Here we have a point load P. See, because of this we have already discussed. Okay, the elastic curve will be somewhat like because of this point load P. See here there is no prevention of rotation because this is a hinge support and here it's a roller support. So this also will rotate like this. There is no prevention of rotation at this point or and this point. Okay, so under this load it will be somewhat like sharpened and it will be like this. So our bending moment exactly will somewhat represent the same shape of the elastic curve. Okay, so this is a sagging case. Sagging case means what? Sagging case means we have a positive value for bending moment. That much we have understood from this. Okay, So we have to draw the SFD first. Before that, we have to find the free body diagram. See, free body diagram of this. Because of this load P, we will have, see this length I'm taking as L. Okay. So we will have, because of this force, we have P by 2 here and P by 2 here. Okay. So shear force diagram will be shear force diagram. Upside we are putting positive, downside we are putting negative. See, a force P by 2 is acting upward. So we have to trace this path of shear force diagram. Here it will be P by 2. Left side is moving upward, so it is positive. Okay. There is no other force till it reaches here at midpoint. This distance is L by 2. Till this point, there is no other forces in order to reduce this P by 2 value. So it goes straightly till here. Here it needs the P value. So P value will push this one till here. Okay, the total force here is P. So the P by 2 is already here. So the other P by 2 should occur here in order to make the total value of here to be P. So then this moves like this. There is no other force in order to increase or decrease this value till it reaches here where a P by 2 value, this value will push it back to its original position. See, this side, this will be negative. This is negative. Okay. So this value is P by 2. So this is the shear force diagram. Now the bending moment diagram. Bending moment diagram will be, this is a hinge here, this is a roller here. So the it will have moment as 0 in these supports. So it will be 0 and 0 here, and this is a sagging case. And because this shear force diagram is like this, parallel to the axis, we have bending moment diagram will be like an inclined straight line. So inclined straight line will be there, and shear force will be 0 in the center. At this point, the shear force will touch 0. So bending moment will be maximum here. This much we can assume from this. So this point we'll have to take. So this value is P by 2 into this distance L by 2. So PL by 4 will be the moment here at this point. From this side also, if you calculate, it will be P by 2 into L by 2. So we will have a moment of, this will be a straight line. We have a moment of PL by 4 here, like this. This is, oh sorry, this is a sagging case, so it should go upside. Okay. So it should go upside like this. The value, this value will be PL by 4. Okay, this is positive. Here it will be 0, here it will be 0. Okay, I hope it is clear. P by 2 into L by 2, that is PL by 4. Okay, so I hope it is clear now. Now we will move to the next question. A simply supported beam having a point load P at center. Okay, I suppose this distance is, this we have already discussed. Actually, the load won't be in center, it will be eccentric. A distance, B distance. Okay, a load P is acting eccentrically. This distance is A and this distance is B. A is not equal to B. Okay, so that is our case. So here you can calculate sigma f of y is equal to 0 and calculate the reaction. I just know it by heart. Okay, PB into L will be the total length A plus B is equal to L. The total length of the beam is L. So PB by L will be the reaction here and PA by L will be the reaction here. I know it by heart, so I'm writing. You can calculate sigma f of y is equal to 0 and find out these reactions. Okay, so that these are the values. Now we will have to draw the shear force diagram. Shear force diagram. See, the elastic curve will be somewhat similar to the other case. It will be like this. So we know that it is a sagging case. So bending moment diagram will be positive. So see the shear force diagram. This force is moving upward. Okay. So here the value will be BB by L. This value will be BB by L. Okay. There is no other force till it reaches here when the P pushes it down. So P will push it down. So here the total value should be P. So we know that PB by L plus PA by L means P by L into A plus B, that is PL by L. So that will be P. So the remaining this value will be PA by L in order that PA by L plus PB by L become P. So it will have a value of PA by L here. Then this load will move like this till it reaches this point where a force of PA by L pushes it back to its original 0 point. Okay, this value is PA by L. So left side moves up and the other side moves down. So this is positive, this is negative. This is the shear force diagram. And now we have to draw the bending moment diagram. The top is positive, bottom is negative. We are taking sagging as positive because this is a sagging case. We have to draw it in the upside. So we will have a value of 0 here because this is a hinge support. It will have 0 value here. And we will have the maximum at this point as we have already discussed. So PB by L into this distance will give you the moment here. That will be PAB by L. So we will have a straight line like this and the value it here will be PAB by L. Okay, this distance is A, this distance is B. So here it will be positive. This will be our bending moment diagram. Okay, so that is it. Now the next question. A simply supported beam carrying a UDL W per length. This is the total length. Because of this load W per length, the total load will be WL acting at the centroid. This distance will be L by 2. So we will have a reaction as WL by 2, WL by 2 here. And there will be zero moment in these points. So this is the free body diagram. Free body diagram will be like WL by 2, WL by 2. Okay, like this it will be. Now, shear force diagram we have to draw. Before that, how will be the elastic curve? Elastic curve will be like this, a smooth curve like this. Okay, so this is a sagging case. So bending moment diagram will be positive. And see, bending moment diagram will be somewhat like the shape of this. Because this is a UDL, we know that our shear force diagram will be a inclined straight line, and our bending moment diagram will be a second degree parabola. That is, this varies as x, and bending moment will vary as x square because this is a UDL. We have already discussed about this. Okay, so the force is WL by 2 is moving up. This shear force diagram above positive, below negative. Okay, so WL by 2 moving up. So the value is WL by 2. Okay, now we'll have to find out, see as it moves at the center, what will be the value? It will be like WL by 2 minus W into L by 2. Till this distance, the load will be acting as W per length here also. So this length per length is L by 2. So the load till here will be, till the center will be WL by 2 because of this UDL. So WL by 2 minus WL by 2 will give you a value of 0 here. So it will take 0 like this. Then after that, the load is causing a negative effect here. It is moving like this till it reaches a value of WL by 2 upside. So this will be our inclined straight line. The above value will be positive, below value will be negative. Okay, so this is our shear force diagram. Now we will have to draw the bending moment diagram. We know that it is positive because this is a sagging case. Okay, so positive, negative. Bending moment diagram, we will have to draw it on the upside. So see here, this is our starting point. Here moment is 0. We know that shear force diagram is shear force is 0 here, so the maximum value of bending moment will occur at this point. Here also it is 0, so this is a second degree curve, so we can draw it like this. And here the value will be, we have to just find the value here, so that will be WL by 2. We'll calculate it. Okay, WL by 2, that is a reaction. From here I am calculating, let it be A. From here I am calculating. Okay, WL by 2 into this distance into L by 2 minus this load is having minus effect. If you take this direction positive, then this will be negative direction. So W per length on this L by 2, this will be having a negative effect. So W into L by 2 will be the load into centroidal distance. This load will act at the center of, if you are taking this particular section from A to the center, we will have the centroid of this UDL at this distance L by 4. So we'll have L by 4 as the centroidal distance. So the value will be WL square by 4 minus WL square by 8. So that will be WL square by 8. So we will have a value of WL square by 8 here. Okay, this is positive because this is a sagging case. Okay, so this is clear. Okay.